In this module, we're going to talk about the method of images and maybe work through a little example to drive that point home. And the method of images is a really clever way for us to simplify problems that involve a conductor tied to ground. So one common situation where that might happen is if you have a charge or some item that's on top of a ground plane. Because the ground plane, it behaves as a conductor, it can take in as much charge as you're willing to give it, but it's also tied to our reference point of ground. So if we have, let's just simplify this situation and have a positive charge here, we can think of the field lines moving like this intuitively, right? So these field lines are, if I have this charge, if you think of this as a pinnacle, a single point, that's at say 100 meters above sea level, and then at this point it's sea level, and you want to draw the slope lines, you could imagine they would, the slope lines would look like this, right? You have a very steep path in the shortest path between the charge and the ground, and then as you move away, it becomes a little bit less steep. Or another way is if you want to visualize the equipotential lines. The equipotential lines look somewhat like that. And then the field lines would be if you drew a line across that's perpendicular to all the equipotential lines. You end up with this. Now, so it starts at 100 meters, and then it all ends up at sea level on the surface of the conductor. Now, one thing that we can do is, the clever trick here is if we redraw a similar situation where we have a positive charge, and let's say this is distance d. If we take another distance d and place a negative charge, what do the field lines look like? So they would actually go like this, and then in the midpoint here, you'll find that in this midpoint here, you'll find that the potential is actually going to be 0. Therefore, if you look at this situation here, the field lines for the upper half look exactly the same, and you don't really care about what happens to the lower half. But what that means is that if I have a grounded conductor and I'm trying to calculate what the field lines look like due to this positive point charge, I can just place the mirror image. So at the mirror location, take away the conductor, and then in the mirror location, place an equal but negative opposite charge, and use my Coulomb's law approach to solve for the solution. And we'll end up with, as far as the region above this upper half region is concerned, you end up with the same solution. Now let's break this down into steps to clarify how this works. So the first step is to identify the mirror images. So let's say that you have a positive charge here and maybe a negative charge here and another positive charge here. Then you would start by drawing out the mirror images. So you would identify, okay, so then I need a negative charge here, a positive charge here, and then another negative charge over here. So once you have the mirror image, the next thing that you can do is you can remove the conductor. So once you have these mirror images, you can remove this conductor so that now all you're left with is a bunch of point charges in free space, which we know how to deal with. So the last step is to just deal with that by using Coulomb's law to solve for the system. So this concept is, it doesn't, in terms of the actual calculation, it's just the first two steps that's new, and identifying the situation. So the situation is if you have a bunch of charges and you have a big grounded conductor and you want to know how to calculate the fields above that grounded conductor, what you do is, again, you identify the mirror images, remove the conductor, and then you're back to doing stuff you know, right? Now it's just an ugly Coulomb's law problem with a lot of superposition.